Robust stacking of convex polytopes.
Robust object stacking is application in a variety of industrial settings. Games such as Bandu demonstrate the human ability to perform stable stacking even with challenging constraints and irregular objects.
Here is the static equilibrium problem formulation. The main constraints are force balance, torque balance, and linear complementarity. It is straightforward to set up a mathematical program to optimize most of these variables. The hard part is developing a differentiable model of contact, which involves parameterizing the contact points and non-penetration constraint. To understand how our contact model works, let us introduce this scenario with two blocks, one in free space and one above the table. We treat the contact points as decision variables and initialize them inside the objects. The 4 contact points are shown in red. We also initialize separating hyperplanes. We then jointly optimize over the contact points, hyperplanes, positions, and forces, and show an example of the optimization process. The blocks are now in static equilibrium.
Having written a complete set of constraints for static equilibrium, we perform the optimization using the SNOPed solver and it converges. We initialize the blocks in the equilibrium state and perform forward simulation. The blocks fall over. What went wrong? Surprisingly, solving the static equilibrium problem as formulated resulted in an unstable solution for nearly half of our trials, stacking just 2 cuboids. The problem is that unstable static equilibria are admitted in our constraints. When the blocks are initialized in unstable static equilibrium, numerical issues may result in imperfect balance and tower collapse. In practice, though, the solutions the solver finds are actually small perturbations from static equilibria due to constraint relaxations. These are not equilibria at all. To resolve this issue, we consider the addition of an external torque robustness constraint. Instead of solving for a single equilibrium, we solve for multiple instances of static equilibrium problem. Each instance shares object poses and hyperplanes, but has separate forces and witness points to compensate for a different torque applied to each body. We find that this formulation converges for 95% of 2 block stacking trials, and all solutions are stable during forward simulation. This animation visualizes the witness points optimized to balance an external torque perturbation of 4 Newton meters. We apply 4 perturbations, 1 in each axis, to avoid unstable edge cases. You can see the witness points spread out in a diamond around the center witness point, which solves for the static case.
Previously, we showed results where we started close to the correct solution and solved locally for equilibrium. This strategy won't allow us to be able to automatically generate many novel towers because we have to solve for each correct initialization by hand. What if we want to automatically generate diverse towers, as seen on the right? We could sample initializations uniformly. However, we find that this never succeeds when there is more than one block. To scale tower generation, we instead sample from smarter distributions. Our strategies include sampling non-penetrating object poses and sampling contact points inside the polytopes. Now we show the optimization process. Here are 5 generated structures. We can see there's a reasonable amount of diversity, especially in the bottom 2 blocks. Finally, we show results for 2 additional convex shapes.